Good morning, Nana, everyone. Yeah, come to the class here. Yeah, good morning. Yeah, I think yesterday we discussed about the moment of inertia of the point masses, different models. Yeah, thin uniform rod. Oh, acha. I completed the thin uniform rod yesterday. Yes, you are right. Yeah, for the thin uniform rod particularly, they will ask different models. Yesterday we got one passing through the center and perpendicular to the plane. Anyone remember? I passing through the center and perpendicular to the plane. Yes. ml square by how much? 12. Very good, Shrestha. And I passing through one end. Anyone remember? ml square by 3. Very good. Very good. Very good. And I parallel to its length, about the axis parallel to its length. 0. Very good. Good, Isha. And then here I making an angle theta. Theta passing through the center is ml square by 12 sine square. Correct. Sine square theta. Yes, correct. Same thing here. The axis is passing through one end and making an angle theta. Will you predict the moment of inertia? Like this, passing through one end and making an angle theta here. What is the moment of inertia? Passing through the center, you know. Passing through one end, I am asking. Yes, Amok. You are 100% correct. Passing through one end is ml square by 3. Okay. If it makes some angle, good afternoon, Nana. If it makes some angle, we got some logic here. That is sine square theta. Yes, ml square by 3 sine square theta. This is the moment of inertia passing through one end and making an angle theta. See here, for the same body, we found almost 1, 2, 3, 4, 5. 5 different moments of inertia depending upon the axis of rotation. So for the same body, if you change the axis of rotation, surely the moment of inertia will be changed. Okay. And here basically almost everything except these two, everything we use the common sense only, using the parallax theorem, These two you have to remember now, derived. Okay. Particularly whatever we get the first moment of inertia, that you must remember, you must verify. The other moments of inertia you can calculate using your theorems. In that one theorem I explained, parallax theorem, I think all of you remember, IP is equals to I passing through the center plus how much? Very good. ML square by 3. mr square, I think. Yes, yes. That is r square. Okay, good. Amok, what? Yeah, yeah. Perpendicular distance between the two axes. Okay, that much shortcut you use. Okay, right. Perpendicular distance between the two axes. Very good, very good. Then here, related to this moment of inertia, where the mass is uniformly distributed, that's very simple questions, Nana. If you understand the question, it is very easy to say the answer. Very easy. But the thing is, you have to understand the question first. Suppose if I say, this is first page only now. Okay. Right here, this is a thin uniform rod. And now I am taking the axis, try to understand his wording, the framing of sentence. Axis is at the midst of half of the length. And perpendicular to the length. And perpendicular to it. To the body. Simple. To the rod. Oh, Sharma, no problem. To the rod. Find the moment of inertia. Take the mass as m, length as l. First, you understood the question, Nana? Here. Anyone understood the question first? Oh, good. L by 4. Good. Yes, sir, a bit. Okay. L by 4 from where, Nana Mok, you are saying? Don't say from left of the body, Nana. Better everything you measure from the center. Center of the rod. Okay, from center will you say? What will be this distance? Yes. Ishan, this is at the center of half of the length. Half of the length is L by 2. In that half, yes, this is half of the length, Nana, L by 2. In that it is at the center, midst, what he said. Exactly at the center means in this half is L by 4. Okay, so all of you understood this one, Nana? Yes, good. Why I said, Mr. Ramok, better you say the distance from the center. We have to assume we are going to take the parallax theorem. In the parallax theorem, yes, in the parallax theorem, one axis must pass through the center. We should not forget the basics. Okay, one must pass through the center means one axis I have to, this is the inevitable condition. I should not take the axis passing through one end. Why? Because surely one axis must pass through the center. That's why I asked you, better you say from the center, the distance from the center. Good. I think this is IC. That IC, all of you know, passing through the center and perpendicular to its length is ml square by 12. Okay. Then I'm asking about the black axis. Okay. Black axis, the moment of inertia, I, about the parallel axis. Okay, parallel axis IP is equals to, you know the formula, IC plus MR square. And you said R here between the two axes, perpendicular distance L by 4. Direct substitution. That's it. ML square. Good. Good amount. ML square by 12 plus MR square. L by 4 whole square. That you will take ML square common. 1 by 12 plus 1 by this 4 square is 16. Okay, 12 and 16, LCM is 48. And after taking, no problem, Nana shows. This is equals to 7 ml square by 48 after taking the LCM. Okay, able to follow this question, Nana, what I said? Okay. Yes, yes, good, thank you. Right. And then here, look at what the moments of inertia of the same body we in theory discuss, and what the numericals they are giving in exam. You observe whatever we are measuring and we are learning here in the theory, we are going to use those formula as the shortcuts in the numericals. Okay. Now look at one more for my sake. If you say the answer for this question, then I will feel so happy and go to the another model. Okay, try to say the answer. Yes, thank you. Try to say the answer for this question. I am taking, excuse me. Sure, Nana, sure, all the best. Aditya, here, take 4 rods at the 4 sides. Means this is one rod, AB, of mass M, length L, and all the 4 rods are identical. Means with 4 rods, I constructed one square. Okay. AB, comma, BC, comma, CD, and AD are 4 identical rods. Okay. Then the question is, find the moment of inertia of the system about a side, any side. About a side means what you understood from this sentence. Okay. Namok, a bit wrong. I think moment of inertia of one body you did not consider. Wow, Charmi Priya, good, correct. AB or any side means, shall I take Charmi Priya the axis like this? This is the axis of rotation. Is it correct? Axis. Okay. Right. Then here, this axis, look at, is passing through the side AB. Then will anybody say the answer? What will be the moment of inertia about the axis for the rod AB? Wow, good. Akhil Amu, correct, 100%. Yeah, Tanisha, correct. Yeah, Ishan, wow, bit late, but correct. AB. Why? Because this is exactly passing through its length and parallel to its length. IAB equals to 0. What happened to Lakshmi Gayatri not respond? Oh, sorry, sir. Lakshmi Gayatri put the answer. Right, 0. Right, good. IAB equals to 0. Will anybody say IBC? This one, this rod. Wow, Amok, correct. The same axis has appeared to be theta 90 or else passing through one end. Simple. Not ML square, Lakshmi Gayatri. This BC, Nana, I'm asking. Tanisha, correct. Okay. Okay, Nana, no problem. BC, yes, Akhil, correct. This is passing through one end of the rod BC. Passing through one end of the rod, formula is ML square by 3. So this is ML square by 3, yes. Okay. And then here, look at for the side AD. How much you say for the side AD? Yes, again ML square by 3. Very good, very good. Why? Because it is passing through again one end of the rod AD. Exactly. Same. Yes, correct. Yes, yes. Yes, correct, Srivali. ML square by 3. Good, Arudra. Now, the leftover one is I of the rod CD. This one, look at the axis is passing through the rod AB, passing not 0, Nana, Charmi Priya. Passing through rod BC, passing through rod AD. But it is completely out of the body. Look at axis is here. Axis is here. And body is completely out, Nana. Look at that. Sure, Nana. Okay, no problem. Okay. Right, mister? Okay, right. Good. Then here, this Sham, I think, correct. This body. Look at Nana, for this body, it is completely out of the body means, yes, we have to take total answer. No stress, I think. Right. That is not correct. Why? Because it is completely out means, first of all, to apply the parallax theorem. No. Lakshmi Gayatri, wrong. Only for DC, Nana, I'm asking. Ishan, correct. Why? Because here, if you assume one axis passing through the center of the rod, given rod CD, okay, then I see about this axis, you can say 0. Why? Because it is passing through the center and parallel to the length of the rod CD. Now, but axis is taken here. So you can use the parallax theorem for the rod CD. Parallax theorem, perpendicular distance, no need to say. What will be the perpendicular distance between those two axes? Exactly equal to side length. Side length is L. Now it is correct, Nana. First time you went wrong, I think. This is L. Okay, right. So according to parallax theorem, I for the rod CD about this axis is IP is equals to IC plus M R square. Perpendicular distance is L square. That is ML square. Now I think everybody can get the answer here. Yeah, correct. Now it is correct, Sham. I is equals to moment of inertia IAB, that is 0 plus BC ml square by 3 plus CD ml square. Yes, now correct, Srivali. ml square plus ml square by 3. Total you are getting 5 ml square by 3. All of you understood the method and how to solve? Yeah, good, correct. Right. Here, such a type of questions, you should get the answers now for the thin uniform rod. Okay. And then here, suppose you take one non-uniform thin uniform, the non-uniform thin rod. If you take, okay, then what happens? Yes, correct. 5 ml square by 3 is correct. Okay. Then for this non-uniform, what to do? Thin rod. Means first try to understand what is the difference between uniform and non-uniform. Okay. Uniform means mass distribution is same at all points. Non-uniform means just like chakris, one side wider, another side thin, and mass distribution is different. One side more, other side less. Mass varies from point to point. Exactly. That's what I'm saying. Okay. And here, since it is thin uniform rod, I'm going to take what here. Suppose its length is L and total mass is M. Right? He says from one end. Okay, suppose you place one end at x is equals to 0. From one end, the mass changes with the distance x as, that one he says, the mass changes over its length with the distance from the left end as what he says, the linear mass density lambda is equals to, they give like A plus bx. Okay. Where lambda is watts are, immediately you ask. That's what I'm saying here. Okay. Where lambda is the linear mass density. Okay. Linear mass density. Who is this linear mass density, sir? Linear mass density means mass per unit length. It is the linear mass density. Nothing, Nana. Here showed us, see, the mass is changing from point to point in the thin uniform rod. That mass, how it changes from left end, I am saying here. From left end, the mass changes according to this formula. In this formula, A, B are constants. X is the distance measured from left end. Then you may come to know an unknown term here, that is lambda. That lambda I'm saying here. Who is this lambda? It is linear mass density, which is defined as mass per unit length. Now you understood? Okay. Right. That mass per unit length in differential form, we write it as dm by dl. That you have to understand. Okay. dm by dl, mass per unit length. Okay. So distance, I take it as x, sir. Okay, take it as dm by dx. That is your wish. Okay. Then immediately you may ask, sir, what is the use of this equation, sir? Simple. Try to recollect what is the formula for moment of inertia. I is equals to integral r square dm. Na? So for substitution here, first you want dm. Na? That dm from this equation you will get. That implies dm is equals to, by taking the cross multiplication, you will get lambda dx. Okay. And able to follow, Nana, what I'm saying here? This differential method for non-uniform distribution. Ah, very good, very good, very good. Thank you. Yeah, right. Good. Then this dm I can easily substitute here. But before starting, in all numericals while deriving, we have to assume one small mass somewhere here. Na? Nana, any student there in our classes, Fayazi? Fayazi. Fayaz is there? Ah, okay, right then. No problem. Yes. Okay, right, right. Then, okay, right, right. Right, no problem. Then here, come to, suppose if I assume one mass, somewhere here, point mass. Okay, no. Yeah, yeah, yeah. Here, this is a point mass. Let it be dm. Okay. And that dm we have to assume from the reference point, he only gave measured from the left end. So from the reference point, I am taking that one at a distance of how much. If I ask, you can easily say the total mass is on the x-axis. That's why this unknown distance, I take it as x. Okay. So here the perpendicular distance, okay, from left end is x. Then immediately I think Amog will ask one doubt. Why you measured the distance from the left end, sir? Where you fixed the axis of rotation? Why? Because here r is the distance from the axis of rotation. Okay. Now I am saying here, okay, going back and saying this is the axis of rotation. Okay. Now I measure that x from where? From the axis of rotation or not? Okay. That's why I take here this x measured as r, the distance from measured from axis of rotation. Then happily I can substitute here the two terms. I is equals to integral r square means x square into dm. From the above equation, I write lambda dx. So able to follow this step here, what I wrote? Yes, okay, right, good, good. Then I write that implies I is equals to, yeah, good. Now I'm going to substitute integral x square. Now the lambda value, I'm going to write whatever he gave here, a plus bx into dx. Just I substituted the lambda value here from the given value, a plus bx. Okay, thank you. Right, right. Thank you. Then here, try to expand this term, Nana. X square into a, that is ax square into dx plus again expand integral x square into bx dx, that is b, x square into x is x cube into dx. Okay, so look at here once. Is it correct, Nana, expansion? If you say it is okay, then immediately we will try to, yes, correct. We will try to integrate the terms. Simple. So a is constant taken out. X square integration, I think you remember, that is x cube by 3. Integration of x square. Okay. And then here b, x cube integration. Correct, Isha. Okay. Yes, Anu, correct. X cube integration is x power 4 by 4. Okay. Axis is taken here means x limits changes from where to where, Nana? From x is equals to 0 to other end, Lakshmi Gayatri. X is equals to 0 to, we have to integrate full rod, no? X is equals to 0 to L. Correct. Up to x is equals to L. So the limits I'm going to substitute 0 to L, here also 0 to L. Okay, then I substitute the limits. A, x cube, that is the L cube by 3, plus b, x power 4. Lower limit I'm not substituting, Nana. Why? Because it is 0. No need to substitute. Okay, directly I'm going to the other one, b into upper limit, L power 4 by 4, minus lower limit I'm not substituting. Why? Because again it is 0. Right. So you are getting finally AL cube by 3 plus BL power 4 by 4. We can stop here. No need to expand this one. Okay, that's it. This is the moment of inertia of non-uniform thin rod. What he asked previously in exam. He gave this one in exam. Simple, we got the answer. Did you find any hiccups and complexity in the middle? No, it is appeared to be, yes, correct. It is appeared to be very simple, very easy. Okay, compared to center of mass, it is easy. Yes, correct. Okay. Yes, likewise, we have to say the moment of inertia of thin uniform rod for uniform distribution. Yes, thank you. Okay. Then here uniform distribution and non-uniform distribution. Okay, good. Then we are moving to another body. Thin uniform rod after completing successfully different models, few applications. Okay, rest of the things you have to solve from the given data. And here coming to the second body. Body 2 we are taking. Okay, that is second body. Thank you. Okay, good. Then we are coming to next body here. That is thin uniform ring. Okay, next body. We are taking ring, Nana, this time. Okay, good. Then why Charmi Akka? This page only? Yes, okay, right. Then here, second body, this is thin uniform ring, simple ring, just like wedding ring, a simple ring. Okay. And that kind of ring I'm taking here. How, sir? Okay, but there is no mass at the center. Ring means hollow part. Okay. This is a ring taking perpendicular to the plane like this. Why? To show the axis on the board. Okay. Look at the axis. First axis should always pass through the center of mass. Center of mass is at the center. That's why here the axis I'm taking passing through the center and perpendicular to the plane like this. This is the axis of rotation. And it is the ring. Having the radius value here I'm taking. Radius this much. It is the radius capital. Okay. So first axis I'm taking. Axis is passing through the center. First axis, once again I'm repeating, must pass through the center. Why? Because that one will be here used in Parallax Theorem. Okay, for the other axis. That's why always we try to derive the moment of inertia about the axis passing through the center. So axis is passing through the center and perpendicular to the plane. Okay, in this case, what is the moment of inertia of the ring? If I ask, it is actually very simple. Why, sir? Look at, if I assume one point mass anywhere on the ring, anywhere, if I assume one point mass here somewhere, suppose I assumed somewhere here, like this, one point mass. Look at any point mass on the circumference of the ring. Why? Because total mass is on the circumference only now. Any point mass is at a distance of exactly, yes, Amok, that's what I'm saying. Exactly at a distance of equals to perpendicular distance is equals to radius. So the advantage is R becomes constant. Any mass on the circumference you assume, that is at a distance of R. I think all of you know, you are very good in mathematics. That too Sharasari is teaching to you. Okay. So I think you can easily understand this point here particularly. So yes, Ishan, that's what I'm saying. I is equals to, okay, you may get some doubt in physics. Why? Because CHAKRI is teaching. But I think there is no doubt in maths. Why? Because Sharasari is teaching. Okay. Thank you. Right. So integral R square dm. Thank you, Sham. That equals to doubt exists everywhere. Oh, it's very smart. Good. Here, this R is constant. Happily, I can take it out by substituting integral R square is a capital R square dm. So simple R square is a constant taken out. Okay. And that is the integral dm. Look at, there is no variable, only one variable there inside the integration. That is a dm only. So happily you can write here what thank you. Integral dm. Simple Manikanta. Last but not least, like Manikanta finally responded today. Integral dm, that is straight away we can write it as m. Okay, m into r square. So happily we can write I is equals to m r square. That's it. Any doubt here writing integral dm as m? Do you have any doubt? No, I think all of you understood. Okay, very good, very good. So see here, just in 1 or 2 steps, we got the answer. Moment of inertia about that axis passing through the center and perpendicular to the plane. That you should not forget. Passing through the center and perpendicular to the plane. Okay. Yes, I equals to m square. So as next body we entered. That's why better we say k also. Radius of gyration. So for radius of gyration, I is equals to I write mk square. Simple amount. You are what you said correct. Mr square. So cancel. I am getting k equals to r. That is the moment of inertia, and this is the radius of gyration about the given axis. Very good. Okay. Sir, where I use this axis as a shortcut if they ask a new problem, sir. Okay, look at here. Suppose this is a nail. Fix it somewhere here. Okay, Varshit. This is a nail. Fix it to the board. Okay. To the nail, one bangle is suspended like this. Like how the calendar we hang to the nail, this bangle, okay, hung to the nail like this. Okay. Nail, sir, where is the nail, sir? That is perpendicular to the whiteboard. That's why I can't show the full nail here. Just I represented with the dot. Okay. So this is the axis of rotation. It is actually nail. Okay. And it is the ring of mass m, radius r. Exactly, Amok. You're right. You're right. Okay. How much you took the perpendicular distance between those two? R. Very good. Then correct. 100%. Example here. This is, or else take the second axis. What is it? Take the second axis here. Axis is perpendicular to the plane of ring like a nail and passing through perimeter. Sir, why you complicate the wording here, sir? Simple. Okay. Axis is simple in mathematics. A tangent, like in mathematics, it is a tangent taken at the surface means that is line taken at the surface is a tangent. Tangent. Yes, Manikanta, I think wrong. A tangent perpendicular to the plane. Okay, tangent perpendicular to the plane means exactly I am taking the axis in the first diagram here, Nana. Yes, correct, 100%. It is mr square only, na? Even. But I took the radius as capital R now. That's why I'm taking here that as m capital R square, not m small r square. Why? Because small r I know as capital R. Okay, good. Axis is a tangent perpendicular to the plane. Okay, look at here. That axis I can show clearly in this diagram like this. A tangent perpendicular to the plane. Now I think compared to the second diagram, you can understand from the first diagram very easily. Oh, the tangent array. Yes, array tangent parallel to the first axis. Okay, first axis. We can use the parallax theorem. Okay, parallax theorem. I is equals to, you can write solution very simply. I is equals to IC plus MR square. You know the perpendicular distance clearly smaller, that is equals to capital R. Therefore, IC passing through the center, you know already, that is equals to MR square plus M into small r is R, capital R whole square. So I is equals to, I got 2MR square. So all of you followed, Nana? This one? Any doubt here? Any doubt? No doubt. Very good, very good. Then last but not least, better you say the radius of gyration also. I is equals to MK square. Here, where you are asking, Nana, Charni Priya, look at the first diagram, you can understand. The axis, whatever I took here, I drew there. Is it 2R or root 2R? Isha, now this time it is correct. Yeah, correct. MK square is equals to 2MR square. Yeah, that implies K is equals to, you can say, root 2 into R. That's it. This is the radius of gyration. Okay. So shall I stop the class here today? Tomorrow we'll discuss none. Okay, not diagonal, the diameter. Okay. Yes. Okay, right now you can come to page number 1 here. Okay. So we'll take